Now let's talk about another research project we have done in a regional framework. This was an assessment of a lot of different technologies designed for space applications. In that case, we worked on health monitoring systems. So the idea was to realize a real-time sensor capable of understanding the propagation of the cracks, the eventual propagation of the cracks into a fuel tank. Of course, the fuel tank is a very crucial device in a launching system. It is realized generally by carbon fiber reinforced polymers. And the problem is that if the tiniest crack is starting to propagate, of course, you take the risk to lose all the mission. The point is that fuel tanks are generally cylinders, if not spheres. So, from the technological point of view, the difficulty is to realize a conformable sensor, something that could be adapted to the cylindrical or spherical structure of the tank. What about the existing systems to monitor crack propagation integrity of the structures? Well, what are the possible transducers that could be used to detect the integrity of a component? The most important one is the strain gauge, which is a meandering resistor whose resistance is continuously monitored. So if you start to deform this resistor along one direction, you are varying its length. And of course, by means of the Poisson ratio, you are varying also its width and thickness. So there is a direct connection between the resistance of the device and the deformation it has. This is the first approach. Another approach is that of other transducers, like for example the piezoelectric transducers. So in this case you use a material which has a property called piezoelectricity, meaning that depending on the mechanical stress applied, you are able to generate a voltage displacement, charge displacement on the surfaces of such material. We will see more in detail later what this means. Another possibility is to use optical sensors, like the fibers. So you have a laser beam which is injected into a fiber, and the minimal variation of the length of the fiber when this device contains a grating produces a variation in the reflectance, the back reflected light. So you are able to simultaneously inject a signal and read out the deformation status of the fiber. There are certain drawbacks of this approach, of course, because the fiber is extremely sensitive to temperature variation. It's also brittle. You cannot apply easily this kind of optical sensors in space. And then there are the resistance-based sensors, of course, the same approach of the piezo-resistive or piezo-impeditive materials. And you have to cope with all the problems related to the space environment, of course. So micrometeorites, atomic oxygen, ionic bombardment, and huge temperature variations. Also, depending on your needs, if you have a real-time monitoring system, you are supposed to read continuously the status. That means that you are also able to use a dynamic system like a piezoelectric material. Why I say this? Because the piezoelectric material gives you an immediate response when you apply the pressure. But if you leave the pressure constant, the charge that is displaced and generated on the surface of the material flows into the circuit, the reading circuit, and soon is consumed, completely absorbed by the circuit. So you are not able to read anymore the pressure level applied on the piezo. You are able to read only the variation of the pressure, the dynamic pressure. While if you use, for example, the piezo-resistive material, you are injecting charge into the material, so you are generating a current first, and the current flows across the circuit and the material itself, and your reading is continuous. So as soon as you have a current, you have a reading of the pressure status. So you can also have static pressure reading. Let's focus on the piezoelectric transducers, because this is the material that we selected to use for the health monitoring of the structures. We have different solutions. The most used one is the piezoceramic material. Ceramic materials are like the ceramic, very brittle. They are generally metal oxides. they have quite good engineering properties. That means that with the very low variations of the thickness or the shape or the volume of the material, the voltage generated on the surfaces of the device is high enough to be read without too much force from the electronic point of view. There is also some issue regarding the toxicity. The most used piezoelectric ceramic material is the PZT, so it's lead zirconium titanate, which is extremely toxic. Of course, the preparation, the fabrication process, and the technological steps that you undergo to realize a device involve the use of human personnel. Of course, it's important to preserve their health. In that case, there are certain solutions like green, so-called green materials, which are not toxic anymore and preserve the environment. So that's what we selected actually. Zinc oxide was the material of choice. Other solutions are the piezoelectric polymers. They are flexible, so this is an extremely good point for the application in the case of health monitoring of fuel tanks, of conformable devices. But they require still a polling process. What does it mean? It means that before using the sensor, you have to apply an extremely high electric field and align all the dipoles, the ferroelectric dipoles in the material. This is to obtain a good remanence state, after which you are able to apply a pressure and read easily a charge on the material. It's more or less the same process that you have for the fabrication of permanent magnets. So you, for example, use metallic powders, you sinterize the powders, applying a pressure and temperature, and afterwards you have to submit the magnet to an external magnetic field. Otherwise, it's completely useless because the magnetic dipoles are not aligned in the same direction. And the macroscopic overall magnetic field is zero because the random orientation of the dipoles within the material cancels each out. No? And the final result is that you have a zero external field. Same applies to the piezoelectric materials. The only point is that the magnetic field is equivalent to the electric field. Another solution is to work with the composite materials, meaning that you have hybrid structures, once again with the polymeric matrix and a ceramic filler, in this case, where you may have both the ceramic filler and the polymeric matrix with active properties. So you can select, for example, both piezoelectric materials. So you can use piezoelectric polymer and a piezoelectric filler. Then you have other problems because it happens, for example, that you have materials with different signs in the piezoelectric constants, and you take the risk to cancel out the effects if the matrix and the filler do not have the same piezoelectric constant sign. What about the typical structure of the device that we have realized? So I told you that in the case of the fuel tank, we have cylinders to be coated, and we wanted to have a fully flexible, conformable device. So we selected the polyamide as a substrate. Polyamide, which is also known as Kapton, which is the commercial name of this compound, it's one of the most performing polymers ever invented because it's able to withstand the temperatures as high as 400 degrees without melting. Its mechanical strength is huge, so it's comparable to certain metals, of course. It's a polymer, but the Young modulus is extremely high. We used this as a substrate. We deposited a typical sandwiched capacitive structure with the parallel plates using gold electrodes. Why gold? Because it is a metal which is not sensitive to oxidation, noble metal that is not reacting with oxygen easily. And in between the two parallel plate electrodes, we placed the active material that is zinc oxide. Afterwards, we used a binding resin, which is kind of glue. In particular, we used an epoxy specifically designed for space application, the Ilantas material, to glue together two polyamide foils. This was done in order to seal completely the device and avoid outgassing mainly. Outgassing is another key issue of the space application. So every material that you use, every device that you realize should avoid excessive emission of gases when you are in the outer space with a cosmic vacuum. Because outgassing could generate, if the satellite is small enough, forces on the satellite, so it can disturb the orbit motion or the position if it's not moving. And of course, it may also pollute the environment around the satellite. So for certain kind of measurements could be a problem. So Kapton is a low outgassing material, which is normally used in a vacuum application, in ground and in space applications. Regarding the process, we use the standard techniques that are typical of MEMS processing. MEMS means micro-electromechanical systems. So the fabrication of devices that integrate functions that are typical of the macroscopic world and that have been scaled down to the microscale dimension. To do so, normally you rely entirely upon optical lithography. Optical lithography is a subtractive method. The idea is that you first deposit the material of choice wherever on your substrate, and then you remove it from the places where you don't need it, leaving only the geometry that you require. To do so, you deposit after the material of choice a photoresist, which is a photosensitive polymer. Then you couple the device with a mask. The mask has certain areas which are completely transparent to radiation, and certain areas which are shaded, and then you submit to UV light. So the photoresist reacts to the UV light, and with a proper chemical bath, you are able to remove the part that was not exposed or the part that was exposed, depending on the fact that you have a positive or negative resist. After this, you have certain parts that are masked by this polymer. You use another wet solution, normally it's an acid, depending on the substance that you have to remove. It's called the etchant system, and you dip your device into this etchant system. Afterwards, you make the stripping, otherwise you remove completely the resist that was remaining on top of the device. And then you start another layer of process. So this idea is very impacting from the environmental point of view, because you generate a lot of chemical wastes, of course, and it's not really preserving raw materials in the sense that you remove part of it. That's the main problem. Regarding the positive effects of optical lithography, it's that you can have extremely high through output, because you can work on wide surfaces. Normally, in research centers, we work with 4 inches diameter silicon wafers as substrate, or in other cases, like in this case, we can work on 4 inches equivalent polymer foils. But the industries are already working with much wider areas. For example, for the MEMS fabrication, they work on 10 inches wafers, and for the silicon chip, much more. So you can process millions of devices at the same time. Also, the resolution is another key feature. The resolution depends much on the diffraction limit. So if you're using, for example, UV light to impress your geometry into the photoresist, the ultimate limit is connected to the wavelength associated to the UV light. So if you want to go below 1 micrometer, you have to use another kind of radiation, in particular extremely ultraviolet, for example, or X-rays. So there are commercial systems that are already using this kind of extremely energetic and extremely small wavelengths to increase the resolution and go down to the hundreds of nanometers.